Ladies and gentlemen, my name is Alexander Pachai. I'm chairing the technical committee for industrial heat pumps in the Euroamon. One of the things that we will look at here is the a little bit of the consideration around heat pumps and a little bit about what we can do and what we will see. So definitions. First of all, what is a high heat pump and what is a heat pump and what is high temperatures and all these kind of things? They are not all totally clear. But generally you can say high temperatures is everything over 100 centigrade for a lot of people. If you look at the standards, it is around 65 and over. So when we also say COP, it's important that we indicate which COP we are talking about. We can be talking about the cooling COP, which is actually also called SEER, and you have also the heating COP, but heat pumps is always COP. And then you have the system COP. And the big challenge for industrial heat pumps in the industrial process is the integration of the heat pump. So you use both sides of the heat pump, both the cold side and the warm side. If you don't do that, you will not use the system optimally. Also, a lot of people, they think a heat pump is just a refrigeration system which is optimized on the warm side. And nothing can be more wrong. If the cold side is not running optimally, the warm side will not be optimal either. And therefore, it's important that you look at the total cycle and understand the cycle. Let's look a little bit about the possibilities, because a lot of people, they always talk about isobutane or in some cases N-butane. Propane in this case is out because it's over 100 centigrade and we are moving up to about 250, you can see. And therefore, there is not a one refrigerant that fits all. COP is one way to measure the refrigerant, but COP is only one of several measures you have to consider. Here you can see we have hexane and heptane as the best, but I can tell you it's not so easy to choose. Actually, butane here is not very interesting if you look at the COP only. But if you then look at the swept volume of the compressor, that you need to do it, then things change a lot, because then you can see hexane and pentane, they have enormous high swept volume requirements for in the low end. And that will make it, of course you can do it, but reality very often kicks in and price makes the trick. So that's why then suddenly butane and isobutane becomes interesting in the low temperature end. But then you can say, okay, why is it that I don't use isobutane? Yeah, it's because I get very close to the critical point is here. So the limit is around 120 for isobutane, and then you can take butane, you can go a little bit higher and still have it running at a decent swept volume. Then we can look at the pressure levels. It's also very interesting. And on this exhibition, you will probably see a lot of ammonia heat pumps. You can see the ammonia, it goes up very quickly in pressure. And that is a little bit a problem for open type compressors. Of course, you could build a semi-hermetic compressor for ammonia. I've seen several on this exhibition. Some of them are prototypes still, but they are coming. And I don't know, but I don't see a need for going so high when you can do very good efficiencies with temperature, with refrigerants that are working at much lower pressures. You can see even water, which is the red stipulated line. It is very high temperatures, and the critical point is 220 bar. When you can do higher temperatures, with the hydrocarbon out here, 380 centigrade is dodecane, and you can do almost the same COP at 18 bar, so it's interesting. So there's many different parameters you have to consider when you want to select a refrigerant for the future. But I don't see CO2 or ammonia going this high. But never say never. Where will the temperatures be used? There is a lot of different temperature levels. This is taken from some publication made by Gordon Abergaus, and you can see that the temperatures range from about 90 and up to 350 degrees for some drying processes. You can probably not see it from where you are sitting, but you can see it when you get the slides, and you can see that there's many different applications. There's also some barriers that we have to consider. In food and beverage, they are very conscious about the flavor, the taste of the products. Take a simple thing as a beer. If it doesn't taste as you expect, then you will never drink it again. And that it can be a problem with temperature, or butter, or cheese, or it can be many things. So therefore, a lot of customers, they are a little bit scared of moving to different technologies and temperatures because of this issue. The most of the big manufacturers in the field, they are ready to do high temperature heat pumps, but the market pull is not there yet, but it is coming, and it's coming faster and faster, and we are trying to cope with it as a producer. Then we have a lot of standards to look at, but they are mostly covering domestic space heating, meaning household requirements for hot tap water. But when we go up in over 100 degrees, there's no real standards covering this, so we have to find a way. We have been looking at different case studies. They are not uniform, they are not in the same way representing. So we tried to collect some of them in a simple way. Then we found out that there is actually a standard for big heat pumps. It is the VDMA 24248, and there is a similar standard for chillers. It's also 2424, but it's 7 at the end, which you can use. But this one is more complete, and you can calculate both chillers and heat pumps. Here I've tried to compare two systems. One is fully indirect, and then you have one with ammonia out in the heat absorber. And you can see with the graphic that comes out of it, a little bit differences in the way you express the COP. So also here, we have different ways of expressing the efficiency, and that it gives it a little bit, but it has to be a standard that everybody can agree to. Otherwise, it is difficult still to communicate with the people that we want to communicate with, and that is the challenge, to roll out this and make people understand what we're trying to promote. But using a standard like the VDMA standard, it's a step of the way. Then we can perhaps move it up to an ISO standard on a later stage. Of course, you can do your calculations in many ways, and one of them is given here by Gordon Abergaus in his book, and there's many other papers showing different ways of calculating. The big challenge is that many engineers, they sit with Excel. Excel is a fantastic tool, but also you can make it stupid by not, you can say poor input also gets poor output. So that's why I'm trying to promote a little bit that we use a standardized way to do it, because it doesn't become better than the input you give. One of the big things in this calculation is to calculate the minimum COP you can use, and that is also, but it's not the same all over Europe, because we have different prices, we have different taxation systems in different countries, so you cannot say this is the truth. The truth is a little bit a variable. So we have a lot of standards for charges. I was just talking to another manufacturer, and he was not aware that you can actually transport systems with a refrigerant charge on board. According to the ADR conventions, you can actually transport a system with 50 kilogram of hydrocarbon on board the chiller without any special declarations. If you go over the 50 kilo, then you have to do a little bit more documentation and advice, and there's some limits on board ships and so on. But below 50 kilo, it's nothing. And the 150 gram that Tommy was talking about earlier is now lifted to 500 in the ISO standard, and it is for indoor systems only. When we are talking outdoor systems like heat pumps, yes, sir. When we talk outdoor systems, there is no limit to how much refrigerant we can have on board the chiller or heat pump. So that is a very important thing to get clear. We also need a lot of new people to do the jobs, because if we don't have the competent persons to do it, then we also have a problem. But there is a lot of people out there that have been used to do boilers, and they are very competent. They just need to be taught what is a heat pump and how do you work on a heat pump, what is the requirements and all this, and then they can go over and work safely, because they're used to work safely with natural gas, which is a blend of other gases. So this is not a big problem for them. Then there is a lot of things around boiler regulations that we have to learn, because our heat pumps, when we get up in these kind of temperatures, they will be covered by boiler requirements, meaning labeling for hot surfaces and all these kind of things that we have to learn ourselves in the industry also. Then there is the whole thing of the integration of the heat pump. You can have different sources. You have to also integrate it so we have the electricity available. And if we have the very big heat pumps, we have to be aware that if you suddenly cut in a big load, it has an effect on the electricity grid. And there is a lot of things that we have to be aware of. So the way forward for big heat pumps will definitely be a VSD, or what do you call it, a variable speed drive to run the machinery. Otherwise, we cannot cut in and out and adjust to the capacity available on the net and mix it with the requirements. So there's many things that we have to look into. Of course, there's also the sources. There is, of course, the geothermal. There is the waste of other cycles in the industrial process, where you can reuse the heat and boost it up to something useful. But one thing is for sure, if you cannot use your waste heat yourself, perhaps your neighbor activity, they can do it. I went to a site in Singapore where we were discussing, but he didn't know exactly what to use the heat for. Then I told him, just across the fence of your garden here, there is a big user of heat. It was Coca-Cola. They use it for cleaning bottles, and they can buy all your heat from you. And he could immediately see the dollars in his eyes. There's, of course, also other ways to reuse heat. You have the organic Rankine cycle. It is still a little bit a niche, and the amount of heat we can recover this way is around 18 to 25%, depending a little bit on what you look at. There is hydrocarbons that can cover the same area as we have done in the past with R245 and whatever they are called, 236. And we can do that also with hydrocarbons and even safe. So in conclusions, the market for higher temperatures is growing very fast. We have constantly people calling us that they want for pasteurization, high temperature pasteurization of milk, it's about 115, 16 centigrade. And there is a lot of drying processes. Drying is a very, very big industry. It can be drying paper, but it can also be drying wood pellets and whatever, and then you burn them. If it is green, I don't know. There is also different ways that we need to publish data that we want to, so we can promote the whole technology, because it's also helping. We have in the ventilation and air conditioning, we have the Eurovent. We have to have something similar for heat pumps for high temperatures. And there's also tools, and one of the tools could be the VDMA 24248. And we can then ask if the customers really want heat pumps. Yes, I think they will, because the gas is becoming extremely expensive. That's one. But you have to remember, natural gas is not here forever. If you start to investigate how much natural gas we have, there is for between, numbers I've seen on the net, it's between 38 and 52 years. It sounds like an enormous long time, but it is very short time if we have to turn around the whole industry to go away from something we burn and go into heat pumps. There is the network, there is all the change of mind, the change of the process, so the beer and the whiskey still taste like it used to do and all these kind of things. So there is a lot of things, and there's a lot of development that we need to do still, but one of the ways is definitely high temperature heat pumps. Thank you very much for your attention. Is there any questions? Any questions? It has been extremely clear. Thank you, sir. I will enjoy all the afternoon with this.